Okay, everyone, so back again to show you how to use the Bessel J function for doing your frequency modulation. Bear in mind that the whole point of using the Bessel is that it's a series of cosines that are weighted by the Bessel function. So in order to pull this off, you have to do a couple of things. So instead of, what I think in class we were trying to, put the limits of integration and put everything into, one function, but in reality you're going to have to use a for loop in order to generate what you're looking for. So I'm just going to do take a couple of things, and we'll do the FFT at the end, and I'll be able to show you where your frequency, or what you're supposed to be coming out to at the end. So I'm just going to set up a random carrier. Our message, it's a single tone, so we're going to do 1000 FS. We're going to do 10 times our sampling frequency, or 10 times our FC, like we did in the previous example. So what I just did there is I'm actually setting up the initial array that we're going to fill in with our Bessel functions. So the next part, I'm going to set up a for loop. So for n, and this is where those limits of integration go, like we were talking about in class. And we'll do 5 beta dot times. And this function here should look just like it does inside of your manual. Give it a second to perform the operation. There we go. And so now what I can actually go ahead and plot this, at least a portion of it. So we're just going to do 50. 50 points of it, because it's a little too large. That's the wrong function. Let's do this again. There we go. It looks like I need a little bit more than that to get something useful. There we go. So you can kind of see that there's some change in your amplitude, and I guess that's probably just not quite. That's a little too far again. I'm going to do. Let's look at something that's a little bit closer. And I could zoom in, but you can kind of see that it's changing, but it's still kind of hard to see. So the next thing you'd want to do to figure out what your magnitude results are is you'd want to go ahead and do the FFT like you did like we showed you in the previous video. However, in this case you have to pay attention, because now our values are much different than they were before. So you have to do the same kind of function. So we're going to say that let's say z equals FFT of y. All right, so now I have to do the same thing that I did before to get that single-sided spectrum. So in this case, we're going to do z, comma, and instead of doing L like we did before, because previously we had identified how many total samples we are, we're going to do length of t, right? That warning is just because I don't have a perfectly even number. So when I did this, it threw in a little exception. It's okay. It'll still plot. And oops, forgot the semicolon. Do it that way. Okay, so now that I have all of that information, I should be able to go ahead and plot this. There we go. So now I have this component here that should be our function. And you'll notice that as I zoom in, this is looking an awful lot like our frequency modulated signal. So now what you're seeing is these are the various peaks, and in order to estimate the bandwidth here, you would just figure out approximately where the total number of components are and find the approximate 3 dB down point. And you can do it right here from the magnitude spectra. So hopefully that helps you figure out how to go about doing this portion of the lab.